Assalamu alaikum everyone. Assalamu alaikum. In this class, we will, this is the continuation of our previous class where we have seen the BPSK modulation scheme, decision rule, and the bit error rate. So, in continuation of that, our second modulation scheme is ASK, amplitude shifting. That was the second in the list, right? So, in this scheme, we will discuss about amplitude shifting, their decision rule. We'll actually first derive the amplitude shift keying equation, the optimal decision rule, so that we can get optimal decision rule. Also, we will see the bit error rate. Okay, just for convenient, let me draw the digital communication receiver. Okay, I have drawn it several times in previous classes. So digital communication receiver. So we actually xt was actually our transmitted signal. The signal is actually corrupted by the noise in t. The output is yt. This the signal is actually corrupted by noise in the channel. So when received as a yt signal is a received signal, it actually passed through a filter. The response of this filter is ht. This is the filter. It's actually LTI system, linear time invariant system. So ht actually the impulse response of the LTI system. The output is a RT. This RT signal is actually sampled at in a sampler with a T. So the output becomes R capital T, right? And here we make the decision. Or detection actually. The detection, right? Okay, so here RT, the received signal, is nothing but the output of the filter is nothing but the yt and its complex conjugate. This actually we did the detail of this equation several times. So for the sake of convenience or to refreshing your memory, I am just drawing it. Okay. Now our modulation scheme is actually the amplitude shifting or ASK. Okay, so so in amplitude shift keying, what happens in amplitude? What changes? The amplitude changes in compared to the phase shifting, right? So we'll actually start from the same equation that our PT, the signal transmitted pulse, is PT equal to 2 by T. We actually write the same equation before for BPSK also. 2 by FCT. I will be very short in this time. T equal to 0 because we already described it. So T is the symbol duration where T is an integer. So T equal to K by FC where K is an integer having a integer value. In our previous cases, the value of k was 2, so 2 appeared in a symbol. Okay. This is actually the same stuff that we also we did in our previous cases. Also in our BPSK we have seen that EP pulse is actually 0 to t. T is the total pulse duration, p square t dt, which is actually was 1 normalized energy of pulse. So this is the energy of the pulse, or this actually normalized energy pulse is unity. So this is actually the energy pulse, energy pulse, energy of pulse. Okay. Now for so far these are the same as the previous BPSK. Now the only difference comes here. For example, xt signal. Xt was A0 PT. Remember, this actually was our signal xt. You also write it several times. X0 equal to A0 PT. Now in this case A0 belongs to what? A0 can be 0 or A amplitude. In our BPSK, the phase changes, right? It was plus A minus A, but this is amplitude. So A0 is either A or 0 in amplitude. In our BPSK, the wave form or wave shape differs in phase, but here the wave form differ in amplitude. That's why the name comes amplitude shift keying. Okay, so same as previously as we described. So for 0 bit, if our bit is 0, this is our information bit. The signal will be A 2 by T cos 2 pi Fc T. This is our for 0. This is for our information B. For 1 is what? So this is for 0. So this is for 0. This is for 1. So for 1 is 0. 0 pt. A0 pt. So 0 pt or 0 into 0 into 0 into pt, which is actually 0. Of course, for both cases, it's actually this is the condition. So these twos are information bit. Info bit. Info bit 0, information bit 1. If I draw, for example, if we want to see visually, so for example, we assume k equal to 2. Remember, 2 cycle per symbol period, so there will be 2. So it will be 1, 2. So this will be expressed, the 0 will be expressed by this. Then again, nothing for 1 is nothing, and again for 0, for example. Right. So 0, 1, 0. This is the way the signal is transmitted. So this is on, this is off, this is again on. So this is signal equal to 0. This is actually signal 0 for 1 information bit 1. Okay, here k equal to 2 and t equal to 2 by fc. Okay, so this corresponds to amplitude a0. For signal 0 means actually it corresponds to signal a0 is 0, for example. For a0 equal to 0, this one, and these are a0 equal to 1. Now you see this is the reason this amplitude shift keying is also called on off keying. On off keying. On off. Oh, okay. So amplitude shift keying can also be termed as on off keying. Okay. Now the question is how to choose this A. How can we choose this A? So we know the bit energy is average bit energy. We know the average bit energy is EB. We actually assumed it, or we fix it, right? Okay, so if this is the case, then for example xt signal has always like two probability two options. One is, for example, if it's 0, then a pt a pt a pt if a equal to or a0 equal to 0, or it can be a 1 bit, which is actually 0 if a0 equal to 1. So 0 and 1 bit. Okay, that's actually we know from this AFK signal. Now what is the probability? So the probability of 0, they're equal probable, is the same as the probability of 1. We actually seen it in also BPSK that probability is half. So what is the average energy per bit? So if I'm deriving the same equation the same way that we did in for the BPSK case. Now it's ASK case. Okay, so an average energy per bit is what? Previously we did actually half a square E P, right? Plus 0, because the other one for this case nothing, so this will be half. Here it differs compared to the previous case. I mean BPSK, it was half a square EP and plus half a square EP. It's actually a square EP. Now we get half a square EP. So average energy per bit, you see, in the previous case it was half. Previous case it was a square EP. I mean BPSK, and for our case it's half. So you can see the half of the energy is this, and we'll see the implication of this. Okay, so if it's half, then half is half. We know EP is 1. Energy. This is unit. This is actually our normalized energy. So EP equal to 1, and if EP is equal to 1, then what will happen? Half of a square. Now our energy, average energy per bit actually is EB. Is actually EB. So EB equal to half a square. So what is A? A equal to twice EB. We also derived for this equation for BPSK. Same equation. only a equal to, probably it was square root of EB, right? Okay. So this energy, the energy, this energy per bit, that's why it's EB, is constant across the screen, is across the, that should be maintained, eh? This cannot be fluctuated. So now we conclude that, okay, if it's 0, we conclude if it's 0 bit, then our signal looks like PT. If it's 1, these are information bit, eh? That 0 PT, which is actually 0, eh? So here both the waveform differs in amplitude, that's why this is called amplitude shift key. From there the name arises. Okay, so question is, what is the probability of error, eh? What is the decision rule and the probability of error? Okay, so from our receiver we can see, from this receiver, yt actually nothing but xt plus nt, eh? So at the receiver we find the, before this filtering, yt signal. So here let me write it. So let me write that yt signal is xt plus nt. So now xt is passed through a match filter, right? So sorry, the yt received signal is passed through a match filter having a response ht equal to p, we know, for maximum signal to noise ratio, pt minus tau, right? Probably, let me check. It is the signal which is pt minus so for maximum pt minus tau, yeah, yes, okay. Now what happened that this signal actually goes to the sampler with t equal to capital T. Sampling frequency is capital T, right? Okay, now we will consider two cases. So consider case 1, consider bit 0. So if bit 0, what is yt? If it's bit 0, yt is nothing but a et is the signal power plus nt, the additive white Gaussian noise, right? So what is the RT signal after? So this signal is here, yt, here and RT after the match filter. Oh, we skip one page more. Anyway, so after the match filter, what's happened? After the match filter, we just seen that our signal will be A, E, P plus this noise will be changed. This noise, So N is no more N. N is N tilde T. You see, we have discussed about this noise in AWGN, this additive white Gaussian noise in our previous lecture, the AWGN, the lecture 3, where we discussed detail about how N become N tilde. Right? So this is actually Gaussian noise where the mean is 0. What is the variance? Variance is n0 by 2. Actually n0 EP, but we know EP equal to 1, so it's actually n0 by 2. Right? Okay. So for this is when we consider bit 0. So again we consider when the bit equal to 1. So what will be the xt? Signal xt actually 0 into pt, which is actually 0. So no transmitting signal. So no need to derive these two equations. Okay. So okay, we can just see what the yt will be. So yt signal will be 0 plus nt will be there. This noise is always adding. This is adding noise, AWGN. So it's actually nt. So what will be the RT for this case? RT is n tilde. This T will be n will be changes h n tilde T n RT. This signal n tilde. Of course, here also this is also a Gaussian with a mean. This will be still Gaussian with here mean 0 and variance is also the same. Variance is equal to n0 EP by 2, where EP equal to 1, so it's n0 by 2. Okay. Now, so for decision rule, okay, let's derive the decision rule for us. So let's derive the decision rule. Decision rule. Actually, it should be the optimal decision rule. For optimal decision rule, let's see what the RT finds. You also derive the same equation for BPSK also. So for RT, we find two things. We find A, E, EP plus N tilde if A0 was A, and we find only N tilde if A0 equal to 0, isn't it? That's actually the summary what we find so far. Okay, now here few things happens. We let me give you this part. This is a Gaussian with mean. This is Gaussian you see the mean of this amount is 0, mean 0 plus this value. So this is the actually the now becomes the new mean, Gaussian with mean AEP. And for this case, is also a Gaussian with mean 0. Mean 0. This was also mean 0, but when we add this one, so mean changes, it becomes a new mean. For both case, of course, for both case, the variance are same. For both case, same variance. Same variance. You see, we have seen the variance are same, right? You see, this is the variance, this is the variance, same variance. So if I draw a probability density function, let us draw a probability density function for both cases. So case for one case, this is the Gaussian distribution. For another case, this is the Gaussian distribution, right? For this case, this is the mean. For this case, this is the mean. Okay, so this is the bit 0. So this is bit 0. So this is the Gaussian distribution. Gaussian for bit 0, and this is the probability density function, which is actually the Gaussian form. So this is okay. Instead of we say PDF, probability density PDF function for bit 0, which is actually Gaussian, and this is the PDF probability density function for bit 1. For bit 1, the mean is 0, right? This is for bit 1. Bit 1. For bit 0, A E P. This is for bit 0, bit 1. Oh, sorry, it's for bit 0. Okay. But here you see their variance are similar. If you find the variance of both cases, the variance will be similar. Now, their what is called the intersection, yeah, or midpoint. Midpoint are not 0. Eh? This is the midpoint. So the midpoint or intersection. Eh? Previously, probably we called it intersection, or we can say midpoint, which is actually a symmetry. Symmetry is what? Midpoint is half of, right? Here the mean value is 0. This is the mean value. So what will be the mean point? Mean value A P by 2. This is the mean point. Now for our case, this is very important. So this will act as a threshold or detection threshold. Detection threshold. You see what we are doing? We are actually trying to find the optimal decision rule. So this is the to derive an optimal decision rule, we really need to know where is the detection threshold. Okay, once we know it, we can easily summarize this rule that for optimal detection or decision, what should be the value? RT is greater than A E P by 2 if RT value is greater than the midpoint, then it will detect A0 as A. Otherwise, A0 as 0. So because in amplitude shifting we have only two possibilities, either A, like capital A, or 0. So if it's greater than 0, it's A. If it's less than 0, So if RT is less than AEP by 2, it's actually A0 will be detected as 0. So this is the optimal decision rule. How we find it? By symmetry. So this is called optimal decision rule. So this is optimal decision. So optimal decision rule by symmetry. The optimal decision rule by. So this is a decision rule. Huh? Now here is up to this is actually okay to have a decision. Okay, we can actually find the probability of error of this mechanism. Okay, but we like to also compare this mechanism with BPSK. So we will actually do little bit more. Okay, now let's see what we can write it in different way. Okay, this is actually, this part is for comparison with the BPSK. Of course, the decision will actually change the form of decision rule, so that because this decision rule we cannot compare it with this decision rule is we cannot compare it with the BPSK system because this is not similar now. So to compare with the BPSK, we had to bring it with a similar nature. Okay. Okay. So we will rewrite this decision rule. Huh? Now here R tilde, we write that this is nothing but RT minus A EP by 0, EP by 2. Okay. So we will use this criteria. If this is the case, or how we can write this R tilde for two different cases. So for case 1, if A0 equal to A, this becomes A E P by 2 plus N tilde, and if A0 equal to 0, this becomes A minus AEP by 2 plus N tilde. Now here actually here so these two actually like this will actually introduce or modify these two so that it becomes similar fashion, similar to BPSK with AEP, right? This is actually now this can be comparable because this is replaced by in BPSK. This was the case, right? AEP by 2. Now in our case it is replaced by AEP by 2. Okay, so all we are doing actually for the case that you can compare it to the BPSK system. Okay. Okay, so for this case should I, okay, if this is the case, then if this is the case if this is the case of R, then we can write the RT. decision. We can rewrite. We can actually optimally we can rewrite this one as this, as follows: RT if is if it's RT if it's greater than a EP by 2, then the decision is A0. So decide A0 as A. If RT is less than A EP by 2, which actually decide A0 equal to minus A. You see, this is actually similar to the for comparing to the BPSK case. Okay, so to decide A0 for our ASK case, so decide A0 equal to A if R prime T is greater than 0, definitely. So what is RT becomes RT minus A EP by 2 greater than 0. So this gives us RT greater than A P by 2. Okay, so now this is actually our decision rule. We finalize the decision rule. Now we like to know the bit error probability or probability of error. Okay, similar to the BPSK case, where this condition, where we actually will use this one, that AEP is replaced by AEP by 2. So what is the probability of error? Bit error, right? So probability of error. So probability of error, PE for ASK, is nothing but the Q function. Okay, nothing but the Q function with AEP by 2 by N0 by 2 EP, right? Okay, for just by modifying it, we can write A square EP by 2 N0. We can write again. We can write, oh, this is Q function. Q function, what can write here? 2, so twice N0. Now here we find EP equal to, we know, 1 and S square equal to twice EP, twice EB. We will replace it. Okay, so by replacing the new PE of ASK will be square root of twice EB by 2 and 0. Okay, now it got simplified. So it's nothing but the square root of EB by N0. So this is the probability of error. This is probability of error for ASK system. Remember what was the probability of error for BSK? It was nothing but the twice EB by N0 in the square root. So we like to compare it. Okay, let's compare. Let's compare with the, so compare probability of error for BPSK with probability of error with ASK. Let's compare and see. Okay, so let's summary here what the probability of error for. So okay, so probability of error for BPSK was Q function twice EB by N0. For our case, now new case, probability of error for ASK, it becomes Q EB by N0. Okay, right? So the what happens here? The Q argument for BPSK, this one, and the Q argument for ASK. To understand that, we really need to know the Q function. What is the Q function? So Q function is nothing but a standard Gaussian random variable, right? So let us draw a Q function. Remember, we have drawn it previously. We did it earlier. So let us draw a Q function. So Q function is a standard Gaussian. Q function is a standard Gaussian, where so Q function is a standard Gaussian with a zero mean. So we say for a value of u, so for the Q function Q u can be written as u to infinity 1 by twice pi e to the power minus t square by 2 dt, because it's a standard Gaussian. It's actually standard Gaussian. So guys, I have discussed about more detail in our previous slide when we have discussed the AWGN, where this standard Gaussian have a mean 0 and its variance is 1. So for that Q function, we see the Q function is a Q as a function of u is a decreasing function. Okay, it's actually a decreasing function. So it's a decreasing function. We can see it from the probability density function of this Q function. Okay. Now, if this is the case, if it's a decreasing function, then Q twice EB by 0 or N0, EB by N0 will be less than the Q function of argument square root of EB by N0, which is actually nothing but the probability of error BPSK then the probability of error ASK. So the probability of error of ASK is actually higher than the BPSK. Now there should be a assumption What is the assumption? That both modulation scheme use the same unit energy. Use the same bit energy. This statement is true if both of the modulation scheme use the same energy per bit actually. Otherwise, if one use less or higher than other, you cannot compare. That's why actually we call it is actually fair comparison. So this EB has to be the same for both cases. Then this is comparable, right? Now, how much improvement we can have by this mechanism? So let's see how much improvement. So for our cases, so we actually let's rewrite it. Rewriting this equation, so Q function. So 2 I can write 2 as a so this is 2 into okay, I write let us write this part. So this will be 2 of half EB by N0 which will be what? Q of EB by N0. What I'm trying to do actually, I try to rewrite this BPSK. I want to make it half. If I make it half energy bit, then I will end up in the ASK. So this one is making BPSK half energy, half EB. Then I will end up to the ASK. So this actually will show us that bit error rate of BPSK for half EB, right? Means actually we will get the same bit error rate by using the half bit energy in BPSK. Okay, so we can say for same bit error rate, BPSK needs half of the average bit energy or EB for ASK. That's actually the argument. So the argument or the conclusion is for same bit error rate, BPSK needs 50%. 50% EB energy per bit. So you see, by when BPSK by using a 50% energy per bit, it will give the same performance of the ASK, right? Which is actually very impressive. It only spend half of the energy, which actually in turns we can write it. I can write it that okay, EB for BPSK is actually half of the EB of ASK, right? Okay, if I convert it to the log, so 10 log 10 EB BPSK is nothing but 10 log 10 half. So 10 log 10 half plus 10 log EB ASK. right? Okay, so 10 log 10 half is nothing but the 3 dB. So if I minus from 10 log 10 energy per bit BPSK minus 10 log 10 EB of ASK is actually 10 log 10 of is minus 3 dB. Minus 3 dB. 3 dB is nothing but half power. That also checks out. That is actually the same bit error rate. The BPSK requires 3 dB lower. So we can actually summarize from here that for same bit error rate, BPSK requires 3 dB less power or less power, less average energy per bit or bit energy, EB. Great. Okay, this is our conclusion when we compare it to the. So we can conclude that the BPSK provides us as actually better performance than ASK. So here we will end. Inshallah, we will derive other modulation scheme in the next classes. Assalamu alaikum.